Okay, so today we will see the portion of Boolean algebra. Okay, now since we have seen and we are aware of the different types of logical gates and their functions and the truth tables, so now we are equipped with to go on with this topic, which is called Boolean algebra. Okay, and this is actually used for simplifying the different digital or binary logical equations. Okay, so this is a different kind of algebra in itself, which is different from the normal algebra that we study in mathematics. Okay, so first of all, it was developed uh, by George George Boole in 1854. Okay, so there are some basic I'll go quickly to the basic laws of Boolean algebra. Okay, so there are some basic laws. Okay, basic laws of Boolean algebra, right? So we can go with this, the first of we have that any logical any a Boolean variable when odd with or when added with 0 will result in that particular variable itself. Okay, so this plus is actually denoting the OR function. Second, we can say that any variable when odd with a high logic value or logic 1 will result in logic 1. Okay, the third says that logic variable plus logic variable itself, plus means OR, so ORing of 1 or 1 is 1. Similarly, a or a will result in a. Okay, so these are simple laws which could be understood by simple intuition and which can be used for simplifying the complex uh, Boolean algebraic equations. Next is a or a bar or a complement will result in always 1. Okay, next is a dot 0 or a and 0 will always be 0. Next is a and 1 would be a. A can be any variable, it can be a, b, c, x, y, z, alpha, beta, whatever. Okay, so it denotes a general Boolean variable. 1 is logic 1 or high value, 0 is logical 0 or low voltage. Okay, then next a and a is not a square but it is actually a. Okay, and a dot a bar is 0. Okay, so we can have proofs for this also, like we can go, suppose a plus 0 is equal to a, so because we know that 0 plus 0 is equal to 0, 1 plus 0 is equal to 1, So observe these two statements. What does this tell? That the result is always same the as the variable which is added to 0. Okay, so we can conclude that a plus 0 is actually equal to a. Similarly, we can prove other uh, laws also, although they does not need any such proofs, but because they are derived from these statements itself, which are actually true. Okay, so for example, let's say that a plus a is equal to a. Again, we will use these two statements itself, like 0 plus 0 is 0 and 1 plus 1 is 1. So from these two statements we can derive that a plus a is actually equal to a. Okay, and this in the similar fashion we can prove each of these basic laws statements. But the thing is that we should remember these basic laws, which are extremely helpful, which will be extremely helpful in simplifying the logical equations later on. Okay. Okay, so apart from this, we also have some other postulates which will be helpful. Again, some postulates like x plus y is y plus x. This is understood. Okay, and the dual of this would be x dot y is equal to y dot x. Okay, so these statements are dual of each other. So duality means the OR operation is replaced by AND operation. Okay, and similar things, when we introduce similar things in the whole expression, we get a dual of that particular thing. Okay, so one is x plus yz, which is equal to x plus y and x plus z, and this is one of the most powerful, I would say. We should remember this anyhow, this statement, that x plus yz is equal to x plus y times x plus z. Okay, and the dual of this would be x times y plus z equals to x y plus x z, which is straightforward. If we open up these brackets, this bracket, we get x dot y plus x dot z. Okay, but this statement is very important. The application of this statement is very it is vast, like it will be used many a times while solving those. So x plus y z, three variables in this fashion can be written as x plus y times x plus z. Okay, And then we have also like we can group them. If x plus y plus z, it can be written as x plus y plus z. The groupings can be done, or the dual of this will be x y z in parenthesis x y times z. Okay, right. Now again one of the most important thing in Boolean algebra is these De Morgan's law statements, which state that x plus y whole complement or prime, okay, is actually equal to x bar times y bar, and the dual of this is x dot y bar equals to x bar plus y bar. So again these two statements, this one and this one, should be remembered like this one. So these three statements are very powerful statement, that is x plus y z is equal to x plus y times x plus z, okay, and x plus y bar is equal to x bar times y bar, and x y bar equal to x bar plus y bar, because these three would be used can be applied to simplify any logical equations. Okay, tell me what will be this one, what will be this one, x plus x y, x, take x common, 1 plus y, so we are left with x 1 plus y, 1 or y, 1 or any variable is equal to actually 1, and x dot 1 would result in x. Okay, so this is how we will use these laws to simplify a logical equation. Okay, so let us see a few examples as to how to reduce the logical equations, or how to simplify logical equations. Okay, so the task would be to simplify these logical equations. Let's take the first example, x plus x bar y is equal to what? So we can write we can perform that law, that a plus y, or just this one, x plus yz is equal to x plus y times x plus z. Okay, so use that statement here, and it will result in x plus x bar x plus y. Okay, and we know that x plus x bar is equal to 1 times x plus y. Okay, and 1 dot any variable is the variable itself, that is equal to x plus y. So this is the answer. Okay, let's take another example. Okay, let's take this one, x bar plus y. So expand this parenthesis, x times x bar plus x y. So x times x bar, a dot a bar was equal to 0 plus x by any variable when odd with 0 is that variable itself, x y, right? Okay, and basically these two examples are dual of each other. Okay, this statement is dual of this statement, and this statement is dual of this. Dual means we replace or with and. Okay, and uh, and then we obtain a dual of that particular equation. So if we compare these two, they are dual of each other. Okay, x or x bar y. So this or is replaced by this and x bar dot y. So this dot is replaced by this plus or operation. Okay, and then we obtain this one, which is dual of this statement. So the result will also be dual of each other. So x plus y would be equal to x dot y. Okay, so let us take the third example, that is x prime y prime z plus x prime y z plus x y prime. This prime means the same thing, bar or the complement. Okay, and I find it more suitable to go with the bar actually, but anyways we will take this one, x prime y prime z plus x prime y z plus x y prime. So what can we do? We can take some common terms like x prime z between the first two terms, this one and this one, this one and this one. Okay, and it will result in y prime plus y plus x y prime. Y bar plus y will be equal to 1, so this becomes x prime z times 1 plus x y bar, and anything added with 1 is equal to that variable x y bar. So this is the answer. Okay, similarly you can go on to simplify this term, x plus y, then x bar plus z, then y plus z. Try to figure it out. Okay, okay, so sometimes we may be asked to find the complements. So like find complement of, let's say, f1, which is equal to x bar y z bar plus x bar y bar z. Okay, and for finding complement we can use De Morgan's theorem. Okay, so it may or may not be stated, so you should understand that what theorem should be applied where. So if it is given, it's fine, otherwise we know that we have to use De Morgan's theorem to find complement of any function. So therefore f1 bar can be found out by x bar y z bar plus x bar y z whole complement. And what were the De Morgan's theorem statements? That x plus y bar equal to x bar times y bar, and x y bar or x bar plus y bar. Okay, so here we can apply this one, that two terms x plus y complete bar equals to individual terms barred and then multiply ANDed. So it will result in x bar y z bar complete bar times or and x bar y bar z, this one. So we have two terms, this one and this term. Again we can apply the second statement, this one, okay, to each of these terms. So x bar y and z bar complete bar is become x bar double bar plus y bar plus z double bar. Okay, apply this second statement, and here also it will become x bar bar plus y bar bar plus z bar. Okay, and x double bar is nothing but equal to x itself. So you can also note it down like one more law, that a bar bar is equal to a itself. Okay, so it will be x plus y bar plus z times x plus y plus z bar. Okay, now you can compare these two expressions, this one and this, its complement form. Okay, they are actually dual of each other. So the complement function of any expression will be the dual of that particular function, and this can be found out by using De Morgan's theorem. Okay, so similarly you also try this and find out the complement for this function f2. Let's f2 be x times y bar z bar plus y z, again by using De Morgan's theorem. Okay, and try to practice problems based on the simplification of Boolean equations, because it will become clear and clearer with practice itself. So practice more and more problems based on Boolean algebra simplifications. Okay, so I will stop here, and we will then meet for the next class. Okay.